Yes, so my name is Marc. I'm a PhD student at the University of Copenhagen, and I'm going to be just presenting how can we leverage deep learning models to integrate different kinds of data modalities into a cohesive representation, what these models promise, and then the actual challenges that we face when we try to sit in front of the computer and actually do it. So, why am I here? I'm here basically because the lab that I joined for my PhD published this paper a couple of years ago, where they were exploring what was happening with this cohort of newly diagnosed type 2 diabetes patients. So they had 800 people, like more or less, that had been super extensively phenotyped. And then they said, okay, let's do some fancy AI on top of that and see if we can find interesting biology out of it. Using this framework called Move that I'm going to introduce in a second. So I'm going to start my talk with the promises that these models actually come with. So the multi-omics variational autoencoder, as the name says, is just it's a variational autoencoder, so a type of deep neural network that tries to, in this case, integrate different kinds of data modalities, including genomics, transcriptomics, metagenomics from the gut microbiome, metabolomics, proteomics, and electronic health records. So a lot of features. And then the idea is that once you have these trained models that have understood the relationships between the different kinds of data modalities, you can start to play with them. Like they are your free playground to see what would happen if you were starting to do, for example, in this case, giving drugs to patients that were not taking these drugs originally, right? So then some of the results that they published in this paper, which was published before I joined the lab, where, for example, here, how does the latent space look like? Like what has this model learned in terms of the structure on the data set? They could also go to feature attribution analysis to figure out which were the key variables that the model was prioritizing in order to understand this kind of data set. Then also, since we had this playground and we could give in silico the drugs to the patients that were not taking these drugs, they were measuring what would be the changes in the gut microbiome composition after giving a certain drug without having to do these interventions in the patient. And also, so since you had the impact of these drugs on all the other omics layers, they could actually bring together different kinds of drugs based on the methods or mechanism of action based on the impact on the rest of the multi-omics. Now, the scope of this project was just to incorporate this machine learning model and try to explore this data. But when I came in with a physics background, and I really wanted to understand how is the model reaching those conclusions. So more on the interpretability side of it. So I started to play a bit with it, but I'm gonna just showcase how the model works with this kind of data that I started to work with at the beginning of my PhD. So here, some patients that went through laparoscopic surgeries were removed some fat samples, and from this fat they isolated adipose progenitor cells, and then they would be kind of stem cell-like cells. They would put them in a petri dish and allow them to differentiate by adding free fatty acids to the cell medium. Or the cellular culture. And then across this differentiation process from this stem cell-like state towards more differentiated fat accumulating cell state, they were measuring gene expression levels, so changes in gene expression using RNA-seq. Also, the morphology, changes in the morphology of the cells, meaning like how do the cells look like? Are there any changes in the way the cells react to this kind of differentiation protocol? Through this technique called lipocyte profiler, which is just a multiplexed, super highly multiplexed microscopy technique. And these patients were also genotyped, so we had access to plenty of different genomic variants, and therefore we could build polygenic risk scores that were relevant for disease. Now, we had around 6,000 features, 300 samples. Now, I trained Move, this variational autoencoder with this kind of data. And the goal with Move is just we have this massive input, we try to compress it into some representation that is easier to handle and lower dimensional, and then we just decompress this information back to input space. So the whole neural network is just trained to get the exact same thing in the output as in the input, while keeping the latent space to be meaningful in a certain way. Now, for illustration purposes, I compressed everything into just 3 dimensions, meaning that now if I plot what's going on, I can see what the model is doing. So no t-SNEs, no UMAPs. This is the genuine latent space. Now, each dot here would be a sample, and it's represented by its latent representation with 3 axes. And what we see is super interesting. So the recipe for training this model was just, I want to minimize the error between input and output. But the dynamics that emerge from these kind of models or model training is not super obvious. So what the model does is basically the encoder brings all the samples that share some sort of label, categorical label, into clusters. And then for the decoder, this task makes it like super easy to reconstruct the different labels, because then it knows that if you come from this region, then you are assigned this kind of set of labels. So this is some sort of emerging behavior that the model does in order to properly reconstruct the categorical features. Now, we see that we have plenty of categoricals, and therefore what the model does is just different boundaries across different kinds of axes. And then for the continuous features, like for example gene expression levels, what the model does is organize the samples based on value gradients. So it just puts samples with, let's say, high gene expression in one side of the latent space, and then low like gene expression on the other side of the latent space. And basically it can this way learn how to represent this feature in this representation space. Now, once we have the model trained and the model has learned how to compress this information into a meaningful latent space, we can perform feature importance analysis, in this case, SHAP. And the idea behind SHAP would be we will remove features one by one to know if they are important for the model. And the thought process here is, if I remove a feature that doesn't really, that the model doesn't really care about, it's not going to have any impact on the representation of the sample in latent space. Whereas if I just remove a sample that is super crucial for the model to understand the representation of this sample, then the sample will move a lot in latent space. If I measure the changes across all the samples in my data set, I can just rank the features that when removed had the major impact on the latent space representations, and then I can know what is the model paying attention to in order to understand what matters in this kind of system of study. Then we can bring this one step forward, or like further, by identifying associations between features by doing in silico perturbations. The idea here would be, for example, for cell type. I have cells of type A and cells of type B, and I want to transition from A to B. What I do is an input switch, so I change the input, I propagate this information through the network, which will have an impact on the latent space representation, and then I decode this information back in the output, and then I just know that I perturbed the cell type, and I also see that gene expression of gene A, C, and D is also going up while I'm doing this kind of perturbation. The impact in latent space that these perturbations has looks like this. Tiny, right? So we have a 1 to 0 or 0 to 1 switch in the input, and we have thousands of features. And the impact that this perturbation actually has on the latent space representations of these samples is really minimal. But what we see is that all of them move from one region to the other, although really little. And I'm going to come back to this in a second. So now we know the type of models that we are working with and how they work from the inside. Now, what are the challenges that we see when doing this kind of analysis? I'm going to first zoom out a bit and just reflect a bit on what are we trying to achieve here. And the idea is that we have different data modalities that provide complementary sources of information. And also, we know that there will be some overlap between these data modalities, but there will also be some contributions that are unique to each of them, and we want to leverage this. Now, when we go and try to integrate these kinds of different data modalities, we face several challenges that I've summarized here. First of all would be data missingness. What happens? How do we handle missing values? Second, how do we handle, or how do we trust that the perturbations that we are doing on these systems are actually mimicking the real life? Then what happens with the fact that we have normally many more features than samples? And then how all of these problems can lead up to problems with generalization and reproducibility of your analysis. So how do we handle data missingness? With Move, it was a really early stage, let's say, pilot. And what they did was impute the values by the mean, so that you just assign some value. And also, when you're training this method, you don't want the method to pay attention to features that you don't have information for, and therefore, they were just not using the information for the missing values to update the weights of the network, so we are not learning from them. The problem with just concatenating all of these data modalities together is that you get an over-reliance on having all of them at the same time, because the model learns the relations between them, and when you don't provide them, the latent representations change a lot. So some improved versions of these kinds of ways of proceeding are these bimodal VAEs, where you just train encoders separately for each of the data modalities, and then what you want is that the representations coming from the different modalities match each other. This has also been applied to single-cell like accessibility and RNA-seq, and the idea is just that you want to leverage this fact that you can predict part of one modality from the other, but also there will be certain things that will be unique to each of the data modalities, and then you don't expect that you can get exactly the representation of one modality from the other. Then I wanted to touch upon a bit the value of the in silico perturbations. So as we just heard, we want to do in silico perturbations to lower the costs. We don't want to do these experiments in the lab. We want basically to prioritize, as was said. Now, what we see, at least with Move, is that there are two claims that you can make. The first claim would be, when I do the in silico perturbations, I see that I change A, and B and C will change in this manner. And this is really clear, or I can know why. So here I'm just showing what would happen if I just went to, if I had a data set and I have gene expression levels, and I have two genes that are super highly correlated, right? Gene A and gene B. So in blue we have the regions where the gene expression is really high, and in red we have the regions where gene expression is really low. Then I go and I perturb gene A in the input, right? I want to see what would happen if I were to increase the expression of gene A. What happens is that then this information is propagated through the encoder, and your samples will move towards the region where gene A is higher. And now these new samples are lying in a region where gene A and also B are higher. So therefore, when I decode it, I will see in the output sample that gene A has gone up, and also B has gone up by doing this perturbation. So the direction of change makes sense. What I have a bit of an issue with is with the claim that we can use these in silico perturbations to exactly get the overall state of the system. So in this case, adding the drug to this patient, and then we see what will happen to this patient after getting the drug. We know the direction of change. We know what features, what proteins, what metabolites might change, but the overall profile, the absolute levels of those things don't change that much. And here we see, at least with our model, that the perturbations go in the right direction, but they never leave the cluster of origin. So you never reach the cluster where you have the patients that were actually taking the drug. And therefore we have to be careful with the claims that we make with these models. Now, I also want to touch upon this super important concept, which is, just imagine a setting in which a wet lab comes to my PI and says we have a lot of data, a lot. And this a lot of data tends to mean that we have plenty of different measurements of plenty of different data modalities on really few precious samples, right? And then the issue that arises from this kind of setting is multicollinearity. And I'm just illustrating it here. So we have proteins, metabolites, PRSs, so polygenic scores measured in just a few samples. If we go and try to represent this information here, like proteins, metabolites, and PRSs, we see that we don't really need 3 dimensions to represent this kind of data set. We are good to go with 2 or even 1 in this kind of extreme setting. And what this means is that there's certain redundancy in this data, and we can always express one column as a function of the others. And it doesn't really matter which. So here you lose all the causality on your predictions, and your model can reach the exact same minimization of the loss in plenty of different ways. And this means that we have a certain uncertainty in the predictions, and the problem is that your model might give you 2 different results when trained twice on the exact same data. Now, a really short detour that I think it's really worth it. This is research by Anthropic, so the guys behind Claude, that have a super nice interpretability team that is not paying me to do this, but still. So what they did is they created this kind of synthetic data set, and we can imagine this to be gene expression levels in a cell. The inputs were really sparse, so normally you only had 1 gene expressed in a sample, and most of them were zeros. And what they did is feed this information through a linear encoder. So they tried to compress this information into a lower dimensional space with a linear transformation. Then what they did, so basically, if you were to feed the samples through this encoder, you would put them in this kind of representation space that can be like a UMAP, for example. Then they tried to reconstruct this back, also with this linear transform going backwards, like just with a transposed matrix. And they trained this whole thing just to minimize the error between the inputs and the outputs. So you want x and x prime to be the exact same. Now, this approach is really simple, and it really tells us something about how this process is going. But it's really neat because each of the columns of this weight vector is a direction in feature space, which means that now if I go to the input and I say, what would happen if I increase gene expression of gene A, the sample is forced to move in a certain super well-defined direction in latent space. And this will be super handy in a second. So the model learns how to represent different input features, like genes, in different directions of the latent space, and the model will also project whole samples to certain positions in the latent space. And then the question to ask is, how does the model learn how to represent my data set depending on how many features do I have and how many samples do I have? So what they see is super interesting because at the beginning, in really low sample regimes, What the model does is, here in red, just try to scatter the samples all over the latent space and say, if you come from this region, you have this feature active, and if you come from that region, you have this other feature active. The features themselves, the blue lines, are not really learned. So this is just mapping certain patients to certain regions in latent space. When you increase the number of samples that you have, it's not worth it anymore to put the samples in different places of the latent space, and the model is really forced to learn how different features are related to each other. And then what we see is that feature vectors are super well defined and samples are mapped to the right place. So why did I just decide to go through this detour in the bioinformatics meetup, right? Because this is pretty much what we observe when we deal with, for example, genotype data. So genotype data, we have how many number, like the copies of alleles that you have at every single variant, and we have thousands and thousands of variants per patient, and we normally, not in the UK, not even in the UK Biobank, have that many patients, right? So then what the model does when we try to compress this information and decompress it again is just bring the samples that correspond to the exact same patient to the same regions in the latent space. And it knows that if you are mapped there, then all of this vector of variants are assigned to you without the need to understanding truly what are the relations between the different features. Back in the day, this was called overfitting. And the problem with overfitting is generalization. So under this low feature to sample ratio regimes, we know that if we want to perform any statistical tests, we will need n, because most of them rely on the number of samples that we have. We have the issue with multicollinearity, meaning that the model can reach completely different conclusions depending on the in different runs, because all of them are equally good. And we have the overfitting problem, which is this kind of memorization, which is easier than actually learning the relations between the features. Now, the way we can fight against this kind of elements is by identifying conserved trends. So basically, regardless of the hyperparameters that I can come up with, like different kinds of architectures or so can I identify associations that are shared regardless of my personal hyperparameter choices? Can I find external data sets where these trends are also observable that are not mine? And also, can I identify different methods that can give me the exact same trends as mine? If I just keep accumulating different layers of evidence, I'm going to be more certain that what I found is not overfitting, but rather something that is real on the data. And on summary, yes, if there's something that I want you to really, like a take-home message is deep learning models do math, not magic. And by this, I mean that first of all, we need to be really honest, like the people developing deep learning models need to be really honest with the other stakeholders. We need to align expectations with our biological, like the wet lab people that come to us that want to use our models, and what can be done and what cannot be done. And second, I also think that the same degree of rigorousness that is asked for people in the wet lab is not asked for us working on AI. And therefore, I think that we need, like if we want to deploy these models in a clinical setting, we really need to be, we need a higher degree of interpretability, and this will come through scientific exploration in the classical sense of these models. Then multimodal data integration is a challenge, as we've seen so far during the morning talks as well. And I would argue that multimodal data integration is really necessary, especially in the age of big data and knowing that we have all these omics layers available for us. So with that, I would like to thank the team that made this build possible, and also Sylvia for inviting me. Thanks a lot, and I will move on to questions.